Hi, my name is Nabil. Today we are going to talk about fractals and how we can use the concept in linear algebra with fractals. So first, we need to give a definition for fractals. It's hard to give proper definition for fractals, therefore I think it's better to give an informal definition of it for now. For that, I want to introduce a concept called self-similarity. It can be defined as a closed and bounded subset of the Euclidean plane in R2 that follows the condition which appear on the screen. This creates some question because some of these terms are quite confusing. What does it mean with closed, bounded, or congruent? To make it easier to understand, I'll show an example for each of these terms. This is how a closed set looks, and this is how a bounded set looks. Next, we can see how a congruent set looks. Two sets is considered congruent when they can be made to coincide exactly by translating and rotating them. Next, we will see some example of self-similarity. A line is considered to be self-similar because we can divide it and the subdivision will be similar to the original line. The s equals 1 over 2 means that the size of the subdivision is half the original line, and k equals 2 means that we divide the line into two parts. The next example is a shape that is not common for us. This shape is called a Sierpinski carpet, and it is self-similar too, with s equals to 1 over 3 and k equals to 8. Now, we are going to give a definition for fractals. Fractals is a subset of Euclidean space whose Hausdorff dimension and the topological dimension are not equal. Again, some questions arise from this division. What does this Hausdorff and topological dimension means? Topological dimension is the dimension that we intuitively think about. For example, a point is 0 dimension, a line is 1 dimension, and a square is 2 dimension. The Hausdorff dimension is a special type of dimension that is quite complicated. But for a self-similar set, the dimension can be defined using a simple formula, which is ln k over ln 1 over s. Following the example before, we can see that a line has a topological dimension of 1 and Hausdorff dimension of 1. Therefore, line is not a fractal. For the Sierpinski carpet, it is given and has been proven that the topological dimension is 1, while the Hausdorff dimension, following the formula, is approximately 1.892. This means that the Sierpinski carpet is a fractals. Next, we will see how we can use linear algebra with fractals. We will be using linear algebra concept to help generate some shape mathematically. Before that, we will introduce a similitude. Basically, a similitude is an image that is produced when the object were translated, rotated, or scaled. Why do we need this similitude? It's because when we can say that an image is a similitude, it is guaranteed that it will be congruent with the object, so it will satisfy the self-similarity definition. The similitude can be defined as a mapping from R2 to R2, which means that it is a linear operator. Now, let's see an example that uses it. We are going to try to generate this Sierpinski carpet. By setting else equals to 1 over 3 and theta equals to 0, we will get the following transformation. Taking 8 values that is on the screen will give us with the coordinates of all the subdivision of the Sierpinski carpet. This is how we can create a fractal using a concept in linear algebra. That's all from me. Thank you.